Thank you. Thank you, Sasikan, for such a nice introduction. I'm humbled. So I'm Ajanta Goswami. I'm faculty at IIT Roorkee, and I'm a native of Assam. And I did my schooling as well as I was born and brought up in Arunachal. So I have traveled around 2,000 kilometers to reach here. And yeah, so it's being very nice being in touch with you all, faculty as well as research scholars who have joined this particular session as well as this particular program. And the main mandate of this particular program is one is just to sensitize you about the use of remote sensing and GIS in different domains and what are the new areas in which remote sensing and GIS is moving on. That is one of the prime objective, sensitization. Second is this is one of the platform where not only you people among yourself can collaborate, but you can collaborate with people like us and those people who will be delivering different type of lectures as well as the coordinators like Sasikan. So we all can collaborate together for some nice research objectives, nice research themes or nice research projects in future. That is what is the aim of this particular program. I was interested with the responsibility of delivering a lecture on remote sensing fundamentals and concepts. And I was specifically told to keep it very simple because maybe few of you people are already experienced in remote sensing and GIS, but maybe there are many people who are new to this particular domain. Although you know very good physics or you are very good in mathematics or you are very good in computer science, but remote sensing in general is maybe a new for you people. So with that particular mandate, I'm starting my lecture. So remote sensing fundamentals and concept. Yeah, so remote sensing. So these are few of the images. These are some aerial photographs which are available in many books, and these are basically stereo pairs that you can see. So looking at this particular image, what you can infer? Main thing is if you can infer that there are some drainage. It looks like there are some drainages, okay? And these drainages looks like the feathers of any bird. It looks like feathers of any bird. So from the general information of geomorphology, if you have gone through the subject of geomorphology, you can infer that any drainage which is got the appearance of a feather, it is called as pinnate type of drainage. And pinnate type of drainage infers what? It can tell us that it is developed over a Lewis deposit, which is Aeolian deposit, or it is above some sand dunes. So from this particular image, we can infer from the pattern, okay? From the pattern or the image elements as well as geotechnical elements, we can make it out that these are pinnate type of drainage pattern, which is a modified drainage pattern of dendritic pattern, and it is developed over some Lewis deposit or some sandbars. If you look at this particular image and specifically if you look at the lower part, you can make it out that there is one particular black spot which looks like some elevated part of thing, which is a volcano. Okay, this is a volcano, and this particular landform, the flat area, is a volcanic deposit. So from association also we can make it out that what type of landforms are there and how that landform has evolved. If you look at this third image, the third image has got many elements to be studied. For example, you can see that there are some layerings. There appears some layering, but these layerings are broken. So these are broken. So what does this broken things indicate? These broken things indicate that these are some fault. Okay, these are some fault. And from this image, you can say that the upper part has got density, higher density, and lower part has got coarser drainage patterns. Okay, lower part has got coarser drainage patterns, the upper part has got finer drainage patterns.
What is it? All participants, please mute yourself so that we can listen to sir's lecture properly, please.
Yeah.
Thank you. Yeah. Okay. So if you look at this particular image, you can make it out that the lower part is coarser drainage pattern and the upper part is finer drainage pattern. So what does it indicate? It indicates that the lower part might be made up of some permeable or porous type of material like sandstone, and the upper part is made up of some less porous.
Oh, sorry. Okay. Sir, you just switch on your mic, please, again. Okay.
Okay. Yeah.
Sorry.
So yeah, the previous image we have discussed that the lower part may be made up of some permeable and porous type of material, for example, sandstone, and the upper part, since the drainage density is very, very fine, therefore it indicates some non-porous or non-permeable material, or less porous or less permeable material, like shell could be there, siltstone could be there, mudstone could be there. This is one of the probability, and these layers, actually these layers indicate these are the tabular structures, and therefore maybe these are some sandstone layers. If you look at this particular image, this is very interesting image. So you could see that this is some indicates some amount, some river, okay, some water body. So some water body or river are coming up, and then through a narrow channel it is passing through, and then it is actually diversifying, and then a city is developed here. So what does it indicate? This indicates that this is a fan deposit. Okay, such type of landform indicates fan deposit, and fan deposit develops where? It develops in those places where from a higher elevation, if a river reaches to a lower elevation, suddenly its velocity breaks. Okay, there is a break in velocity, or the velocity reduces. Since the velocity reduces, so all the sediments will be deposited in a fan shape. Okay, in a fan shape, and it could be hardly 5 to 10 degree in slope. The slope may be 5 to 10 degree, and these fan shaped deposits are called as alluvial fan, and there are many cities which are developed on alluvial fan. So this particular image is of Chandigarh area, which is developed on an alluvial fan. Similarly, if anyone has come to Dehradun area, so you could recognize that Dehradun is made up of two fans. One is the Dehra fan, another is the Donga fan. So there is the merging of two fans, Dehra fan and Donga fan, and it has got a slope of 5 to 10 degrees. Okay, it has got a slope of 5 to 10 degrees. Similarly, there are many fans like Kosi mega fan. It's a mega fan, which is not easy to perceive in ground. Rather, when you are studying it through remote sensing, you can make it out that how big that particular mega fan is and what is the geomorphology of that particular area. So towards the end part, you will have finer sediments. Towards the upper part, you will have coarser sediments. I'm just going through all these images first so that you get acquainted with what we exactly do with remote sensing. This particular image is of a glacier. It's a glacier, and this is a glaciated area. This is called as Satopan Glacier. This is called as Bhagirathi Khadak Glacier. So there are two glaciers here, Satopan Glacier and Bhagirathi Khadak Glacier, and together they converge here, and from here the Alaknanda River originates. So this is the origination of Alaknanda rivers. So this landform shows that how a glaciated area could be seen in case of remote sensing images. If you look at this particular image, which is from Dehradun area, you could see that there is one reservoir. Okay, there is one artificial damming here, and because of that damming, there is a reservoir which is created. Okay, some water are trapped here. So such type of landforms also you can always study. This is again one more interesting picture which shows, or the image which shows karst topography. And these black spots, these indicates sinkholes. How we could say these are sinkholes and not volcanism or volcanoes? Because if you look at the stereo pairs, you will always see depression. And this depression indicates that these are sinkholes. And these sinkholes, if you plot it, you will find that these are along some lineaments or crossing of lineaments. And they all are aligned along the crossing of lineaments. It means these sinkholes are structurally distributed. And the other part, which is the northeastern part, the northeastern part indicates some amount of drainage which are not influenced by karst topography. So maybe these are the sandstone terrain. Okay, why? Because the drainage are coarser. So after going through all these images and understanding what exactly is there in all these images, let's try to understand that what is remote sensing, why we do remote sensing, how we do remote sensing, how it has evolved, and how to collect data, types of remote sensing, and what do we sense. So initially the first part will cover this particular aspect. Then we will go for the physics of remote sensing. Then we will go for the atmospheric interaction of electromagnetic radiation. And finally, we'll discuss about the resolutions of images. That's what is the total distribution of this particular lecture. So let's go to the first part of this particular lecture. So what is remote sensing? So whenever you do, all of you are scientists, isn't it? You all do scientific research. So what we do in scientific research? In scientific research, we do data collection. Okay, scientific data collection. So what is scientific data collection? Scientific data collection is based on three particular aspects. The first is we need to observe. Okay, we go to any river and we try to observe that how the water is flowing. Then we try to measure. We try to measure how much amount of water is flowing in that particular river and for how long it is flowing, and what is its delinearity. It means per day how it is changing, and what is the seasonality. And then we try to find out what is the, we try to collect the data. So observe, measure, collect data. Three things, please remember. These three things could be done in two ways. One is in situ, it means we go to the ground and then we collect data. or we do remote sensing analysis. It means from space or from higher up, we can collect those data. So we collect what? Observe, measure, and collect data, scientific data, and that could be done in situ or it could be done using remote sensing. So in situ or on site, what are the advantages? When we go to on site, the major advantage is we know exactly what we are measuring. Okay, so for example, whether we need to measure the water flow or we are measuring the temperature of ice, we know exactly what we are measuring. But there are certain disadvantages. First is the observational error or human error, because whenever you are observing, there could be some amount of human error which is incorporated into your data. Second is intrusive. You are intruding the system. It means if you are going to a glacier and then you are measuring the temperature, so there could be some intrusion of human temperature also. So there is intrusion. Inconsistency in technique. If two different people, like you research scholars, whoever are attending, if two research scholar groups are going to one particular area and they are doing same analysis using two different instruments, there could be some inconsistency in the technique, and because of the inconsistency, you can have different results. Limited coverage. You could have limited coverage. You can't cover the whole area at a time. How much area we can cover? Some 10 by 10 kilometer or even less than that. So these are some disadvantages. So now let's understand what is remote sensing. From the initial definition, whatever I defined initially, from there, what we said that observe, measure, and collect data. So we can say that remote sensing is a science of observing, measuring, and collecting data of an entity or object without touching it. So what is remote sensing? The science of observing, measuring, and collecting data of an object or entity without touching it is called as remote sensing. So it is from a distance. Okay, it is from a distance. And how far that distance is? That distance could be few meters or within a meter if you are using spectroradiometers, which is ground-based information collection, or it could be few kilometers if you are, or few hundred meters if you are using UAV, or it could be few hundreds of kilometers if you are using satellite data, or few kilometers if you are using aerial data, aerial platform. So distances varies, and highest distance for terrestrial remote sensing is some 3,600 kilometers. Okay, 36,000 kilometers. That is the highest distance from where we can do remote sensing, terrestrial. But if we do planetary remote sensing, it can go to further distances. So the definition, the science of observing, measuring, and collecting data of an object or entity without touching it is just a layman definition which encompasses most of the thing. However, there is a scientific definition of remote sensing. What is that scientific definition of remote sensing? If you have gone through the book by Lillesand and Keffer, 1994, it's a very popular book on remote sensing. And I suggest you all that if you start remote sensing, then do go through this particular book. They defines that remote sensing is science and art of obtaining information about an object. It is both science as well as it's an art of obtaining information about an object, area, or phenomena. What type of phenomena? For example, recently the cyclone came, yes, isn't it? Before that, there was one more cyclone in Arabian Sea. So these are some phenomena. So if we are capturing those phenomena also, still we can use remote sensing. So the remote sensing is science and art of obtaining information about an object, area, or phenomena through the analysis of data acquired by a device that is not in contact with the object, area, or phenomena under investigation. So here, the only difference is from my previous definition that now phenomena is also included. Phenomena is also included in the definition. So that is what is the complete definition of remote sensing. Fine. So there are different types of platforms, like the platform could be field spectroscopy, it could be aerial photography, or it could be Earth orbiting satellites. So field spectroscopy means within a meter, we are the distance is within a meter, okay, from the object. Aerial photography means few kilometers, and Earth orbiting or satellites means few hundreds of kilometers or thousands of kilometers. Advantages. There are many advantages. First of all, we have systematic data collection, means whatever data we are collecting, these are systematic. Information about 3D of real objects. We are getting information about the 3D of real objects. For example, how high is the Eiffel Tower? How high is Mount Everest? Okay. So all these 3D informations we used to get from remote sensing data. It is the only solution sometimes for the otherwise inaccessible areas. For example, if anyone have heard about the recent incidents which took place in Chamoli district of Uttarakhand, where there was a huge glacier break. Okay, there was avalanche, and due to that avalanche, 2 hydropower projects completely washed out, and hundreds of people, or around 200 people, died in that particular incident. So all the preliminary information, all the informations that we got were only from remote sensing, and the initial papers, initial solutions, okay, all this came from remote sensing only, because it was not possible for people to go there. Most of the roads or bridges were damaged in that process. Global coverage. We have a global coverage. Repeatability. So remote sensing has got a repeatability, like every 15 days, every 1 day, every few hours, or even maybe a longer time also. So there is a repeatability. It means for a long time consistently we can study that particular phenomena or object, and we can have a database where we can do change detection also. Multi-purpose information. We get information which is multi-purpose. It means it is not only for hydrology, it could be for geology also, it could be for urban planning also, it could be for disaster also. So whatever information we are getting, it is multi-purpose. Synoptic view. Since we are getting the information from top, so there is a synoptic view also. It is cost effective. Only cost of doing remote sensing is sending your satellite to the space, and once it is launched and once it is revolving in this around the earth, so after that, whatever image it is acquiring, it is of least cost. Only the maintenance part is going on. Okay. Yeah. So sensors can measure energy at wavelengths beyond range of human vision. So we can only see objects from 0.34 micrometer to around 0.7 micrometer. But when we are using remote sensing, so we can see beyond that. Okay. We can use the entire range of electromagnetic spectrum. And then we can see that how different type of objects could be seen in different parts of electromagnetic spectrum. When we say seen, in that case, we are talking about the reflected energy only, and reflected energy could be seen only up to 2.5 micrometer. Not seen, but measured. Beyond 2.5 micrometer or from 3 micrometer onwards, it is emitted energy. So in that case, we talk about the temperature or brightness temperature. So there are two differences. That I think the future lectures on hyperspectral and thermal remote sensing people will cover. And then near real time. This data is near real time. So these are few of the advantages of remote sensing. Now, remote sensing could be satellite remote sensing or aerial photography also. These are some very common questions in UPSC I have seen. So what is the difference between satellite remote sensing and aerial photography? When we do satellite remote sensing, the speed is very high because it is orbiting in the space. Therefore, the speed is very high and we have got high temporal resolution. For example, if we go for geostationary satellites, we can get data every 15 minutes or every 5 minutes or every half hour. It's with that speed. But if you are taking polar orbiting satellites, so like NOAA data, MODIS data, we get some, initially we were getting some 12 scenes per day from NOAA data. Why? Because there were some 4 or 5 satellites which were orbiting around the Earth. But in case of aerial photographs, the speed is very limited. It is slow and it's more time to cover an area. So aerial photograph, the speed is less. Satellite remote sensing speed is more. Level of details. So level of details in case of satellite remote sensing, it may go up to 50 centimeter in GeoEye. But if you look at the recent Cartosat data, I think it goes up to 15 centimeters, if I'm not wrong. You can just browse through it. So it has got more higher details actually. So you can achieve up to that much of detail, spatial resolution. In case of aerial photographs, actually, we get even better. Okay, you can get even better. It means we can go up to 2.5 centimeters. And in fact, that particular relation, spatial resolution depends on 2-3 more factors. One factor is the height from the ground, and then the IFOV. Okay, what is the angle of IFOV? Upon these two parameters, actually, the spatial resolution of any aerial photographs or any UAV depends. Weather condition. Weather condition is during cloud. When cloud is big, it hinders the optical remote sensing. That is the one major disadvantage of optical remote sensing, not satellite remote sensing, but the optical part. In case of aerial photographs, the advantage is that if there are some high cloud, so your aircraft can flow below the high cloud. So in cloudy time also, you can have many data. Location. Satellite remote sensing, there is an international treaty. You will get cross-border images also because it has got large swath width. But aerial photographs, you can't cross the border. And therefore, you need lots of permission. So you can do only remote sensing of your country. That is one of the disadvantages. Post-processing of satellite remote sensing is a bit easier. Why? Because we get a single scene which covers a huge area. For example, if you take list4 images, list4 image, the recent resource set list4 images, they are around 75 kilometers. The swath width is around 75 kilometers, which is quite huge. Okay, so it means you get such a big area at a time. But in case of aerial photographs, you will get very small patches. And all the small patches you will have to mosaic and then you will have to process. So post-processing is very tough. It's very tough in case of aerial photographs compared to satellite remote sensing. Then there are two different remote sensing. One is called as active remote sensing, another is called as passive remote sensing. What is active and passive? As the word itself says, passive remote sensing means when the source of energy is external. It is not internal. External means, for example, sun's light. Okay, and active remote sensing means when the sensor itself has a source of energy, then it is called as active remote sensing. So in case of passive remote sensing, it employs external source of energy, And active remote sensing has its own source of energy. Or then it measures either reflected, so passive remote sensing measures either reflected radiation from sun or emitted radiation from the surface of the earth. So the optical remote sensing, they have got a limitation that it could be done only during daytime. Optical remote sensing up to 2.5 micrometer, because it depends on sun's reflection, sun's energy and its reflection. However, the thermal remote sensing, okay, thermal remote sensing, which is from 3 to around 20 micrometer, that range, it has got both day and night operability. Why? Because it senses the energy which is emitted by the surface of the earth. So emitted energy can work both at day and night time, although its scale can be different, its intensity could be different. That's the other thing, but otherwise it has got day and night operability. The passive remote sensing suffers from variable illumination conditions of sun and influence of atmospheric condition. Why? Because it depends at what angle the sun is looking at your earth surface when the image was taken. And every season it keeps on changing. Therefore, there is a variable illumination condition of sun, which influences atmospheric condition. In case of active remote sensing, there is controlled illumination signal and day and night operation is also possible. So these are few of the advantages. Then I just gave one example, like conventional camera, it is an active sensor or passive sensor. So if we are doing using our camera during daytime, so it is a passive sensor. When you are using flash, it is an active sensor. So the whole process of remote sensing could be broken down into these 6 steps. The first is the energy source or the electromagnetic energy striking the target, which is your sun. So first we need a source of energy. Then radiation and atmosphere, it means interaction between radiation and atmosphere. So the sun's energy, it travels through the space, which is vacuum. Then it enters our atmosphere, where there are lots of gases, molecules, as well as water molecules are also there. So while entering into the atmosphere, it interacts with the atmosphere. Okay, there are lots of interaction that we will be discussing in coming slides. And then some amount of energy, it touches the surface of the earth and it interacts with the surface of the earth. Then it is some amount of energy is radiated back. Whichever amount of energy is radiated back, it again interacts with the atmosphere, and then some amount of energy reaches the surface, the sensor. Whatever energy reaches the sensor, we measure that thing only. So there is radiation and atmosphere interaction. That thing also we need to study. Interaction with the target. So all the targets have got different type of interaction. For example, if the surface is very smooth with respect to the wavelength of the electromagnetic radiation, so in that case we can have specular reflection. It means everything will be reflected back. So it will look very bright, for example, a mirror. Okay, but if the surface is not smooth, it is rough with respect to the wavelength. Okay, please remember I am saying one word with respect to the wavelength. Okay, so roughness is a function of wavelength. So when the surface is rough, so we can have Lambert-Eaton reflection or diffuse reflection. It means the energy of the electromagnetic radiation which is striking the surface will be scattered. It will be scattered and only one part will be reaching the sensor. So these interactions also we need to study. Then recording by sensor, whatever energy is recorded by the sensor or the information is recorded by the sensor, transmission of that particular information, and reception and processing. So whatever is recorded by the sensor, it is transmitted to the Earth Observation Center. Okay, so from the Earth Observation Center, what they do, for example, NRSC or any other organization, they used to pre-process that particular image. Whatever information they collect, they used to pre-process it, and then they used to give it to the users like us. And what we do the interpretation and analysis. If there are some people from computer science background or any people from physics background or any people from mathematics background, then you can do what? You can do not application, but you can do some technical modifications of that particular data, manipulation of that particular data, or processing of that particular data. So these are not application, they are technology development part. You can do some technology development part, but the other people like geology people, agriculture people, forestry people, most of the time we used to do the application part. We are focused on the application part. Okay, so with this particular prelude, let's now go back to the one important content, that what are the basic physics which we need to know to understand remote sensing. Okay, very basic physical laws that we need to know your remote sensing. So we'll go through it very quickly because I presume that most of you know everything about the basic laws of electromagnetic radiation or the physics of electromagnetic radiation. So if we talk about remote sensing, in remote sensing we sense what? We sense the electromagnetic radiation. Why? Because electromagnetic radiation is the only source of energy which can travel through vacuum and or space. So sun's energy is reaching to Earth. So most of the time it is traveling through vacuum or space, isn't it? only through atmosphere, it has got some amount of interaction with the gases. Similarly, the satellites which are at some orbit, some 450 kilometers, 500 kilometers. So major part of its distance is actually vacuum. Only some part is covered by gas or air, which is our atmosphere. So it means the energy which we are sensing through remote sensing are basically electromagnetic radiation. So what are electromagnetic radiation? Electromagnetic radiation could be defined by wave theory as well as particle theory. The wave theory considers electromagnetic as what? It considers that electromagnetic radiation is a harmonic sinusoidal wave, as you can see from this particular GIF or GIF file. So it is considered as a harmonic sinusoidal wave according to wave theory. Then there is a particle theory. What is particle theory? Particle theory considers that electromagnetic radiation consists of many discrete units or photons. So particle theory believes on photons and wave theory believes on harmonic or sinusoidal waves. And how this moves, the electromagnetic waves propagates in one particular direction, and it has got a magnetic field and electric field which oscillates perpendicular to the direction of propagation of that particular energy, as well as perpendicular to each other. Okay, so this is a transverse wave. This is a transverse wave. Why? Because the electric and magnetic field are perpendicular to each other. At the same time, they are perpendicular to the direction of movement of the EMR. So the both wave and your particle theory could be combined together, and it is said as the energy is emitted as photons, but its statistical distribution over time is described by a wave. Okay, so it encompasses both the definition, wave theory as well as particle theory. So it's a electromagnetic radiation is a form of energy with the properties of a wave, and these waves propagate through time and space. It propagates through time and space in a manner rather like water waves, but oscillate in all directions perpendicular to the direction of travel. If you have seen waves in water, so similarly electromagnetic radiation also propagates through both time as well as space in all directions. But the only thing is here, oscillation in all direction is perpendicular to the direction of travel. It means the electric and magnetic waves are perpendicular to the direction of travel. Second most important thing is that it can travel through vacuum also. The most important thing is it can travel through vacuum also, unlike the sound waves which cannot travel through vacuum. So electromagnetic wave is a transverse wave in the electric field and a magnetic field at any point in time in the wave are perpendicular to each other as well as to the direction of propagation. And virtually all energy exchange between Earth and the universe is through electromagnetic radiation. It means whatever energy our Earth is actually exchanging with the space, with different type of stars, or with the universe, it is only through electromagnetic radiation, or it is majorly through electromagnetic radiation. So this electromagnetic radiation, if the short waves, if you look at the short waves have got high energy photon, long waves they have got lower energy photon. Okay. The concept of electromagnetic waves were first suggested by 19th century physicist James Clerk Maxwell. I'm not going through all these details. You can always go through basic physics. Okay, and I can skip few of these things. So let's go. Let's look at this particular wavelengths, different type of wavelengths. So the shortest wavelength or the smallest wavelength represents gamma ray. Then there is X-ray. Then there is ultraviolet ray. Then comes the visible spectrum. This is a very narrow spectrum, some 0.34 micrometer or 0.4 micrometer to 0.7 micrometer, within which we can see. It means the whole spectrum we can't see. We can see only a very narrow window. Then comes infrared, which is quite bigger one. Why it is bigger one? Because it goes up to 100 micrometers. Okay, it's very, very big one. Then comes microwave, and then comes the radio wave. As we move towards microwave and radio wave, the wavelength increases tremendously. The wavelength increases tremendously. So short here, if you come here, they have got shorter wavelength, higher frequency and higher energy. If you look here, longer wavelength, lower frequency and lower energy. Okay. So the thing is, we can't do remote sensing of ultraviolet, X-ray or gamma ray. Why? Because ultraviolet and all these rays are actually mostly absorbed by UV, absorbed by ozone. Okay. So only small part of ultraviolet and larger part, all part of visible and then beyond are actually has got transmissivity, or it can pass through the atmosphere. Otherwise, most of the things are absorbed by the atmosphere, and therefore we can do remote sensing of only visible spectrum, few parts of infrared spectrum. Why few parts? Because most of the part of infrared spectrums are absorbed by water molecules, or it is also absorbed by what? It is absorbed by carbon dioxide also. Okay, and then comes microwave, which is completely a different domain. So the electromagnetic waves can be characterized by two principal measures, which are the wavelength and frequency. And wavelength is the distance in meters between successive crests of the waves, and frequency is the number of oscillations completed per second. So if you look at this particular representation, you all have gone through basic physics, or even up to class 10 or 12 levels also it is taught that there is one amplitude, then we have wavelength, and then there is a frequency. So what is this? Wavelength is length of one wave cycle, which can be measured as the distance between successive wave crest. So successive wave crest or successive wave trough. So crest or trough, if we measure, we get the wavelength. Frequency is if in 1 second how many cycles are completed. That shows frequency. If higher number of cycles are completed, higher frequency. If lower number of cycles are completed, lower frequency. Amplitude is the height of this particular wavelength. Okay. There is a relation between wavelength and frequency, and this relation is also the speed of the light, which is c equal to lambda multiplied by nu, and where lambda equal to wavelength and the nu is your frequency. There is cycles per second or hertz that I have already defined here, that how many cycles are completed in 1 second. For example, 1 cycle, 2 cycle, 3 cycle, so 3 hertz, like that. So light does not require a material medium for its propagation, as I told earlier, and the speed of light through vacuum is 3 × 10⁸ meter per second. So EMR, if we study from particle nature theory, so in quantum concept, the radiant energy depends on number of photons, and the energy of a photon is given by energy equal to h multiplied by mu, which is h multiplied by c by lambda. So but both by this equation we can define. So from this equation we can see that if you remove h and c, so E is inversely proportional to lambda. It means energy decreases as wavelength increases. So that defines one particular concept that we will be discussing later about spatial resolution, that since energy decreases as wavelength increases, therefore if we measure, do remote sensing of bigger wavelength, for example thermal bands, so in that case we get lesser energy, and since we get lesser energy, therefore we need to compromise with the spatial resolution, and that is why thermal bands have got lower spatial resolution compared to visible band. This is the relation which defines that thing. So what is the scientific convention of measuring different type of wavelengths? Radio and microwaves are usually described in terms of frequency or in hertz. Okay, so radio waves and microwaves are usually described in terms of frequency or hertz, because in terms of meters it will be a very big number, and therefore it is done in case of hertz only. Infrared and visible light in terms of wavelength in meters. So infrared and visible lights we generally define, or we the units are in meters. For radio and microwave it is in frequency in hertz. Infrared visible we generally do it in case of meters. X-rays and gamma rays in terms of energy or electron volt. So when we define X-ray or gamma ray, we generally go for energy. We define in terms of energy or electron volt. Why we do this? This is a scientific convention that allows the convenient use of units that have numbers that are neither too large nor too small. So this is just a scientific convention, and therefore we use such type of units because it helps us to actually keep it within a certain number. It is neither too large nor too small. Okay, so always remember, radio and microwave, whenever we will be defining, it will be in terms of frequency or hertz. Infrared and visible band in terms of meters. X-ray and gamma rays in terms of electron volt. Now let's try to understand few spectral radiometry. What are the spectral radiometry? So here we will be discussing about different type of radiometric quantities, and then measurement geometry like concept of solid angles. Very quickly we will go through it. Okay. So I told you that we measure electromagnetic radiation. So you could say that, sir, what exactly we measure in electromagnetic radiation? You have talked about energy, you have talked about speed of light, so many things you have talked about. So what exactly you measure? So see, any electromagnetic radiation, it has got certain amount of energy. So here I have defined E equal to the energy. So what is this energy? This energy is in joule. Radiant energy could be defined in terms of joule. When we add time domain to this radiant energy, okay, so it means radiant energy per unit time, per unit second, per unit hour. So then it becomes the power of the electromagnetic energy, which is called as radiant flux. Okay, so we have a radiant energy. When we measure radiant energy with respect to a unit time, or we are adding the time domain, then we get the power of the particular electromagnetic energy, which is called as radiant flux. And flux is measured joule per second, or it is also called as watt. Okay, so when this particular power or radiant flux, we add time area, Okay, we have a time and then we add area. So what is area? It means per unit surface area, okay, per square meter. So when we add area also, first we have added time, then we are adding area. So what we get? We get flux density. Okay, so when to radiant energy we add time plus we add unit surface area, we get flux density. And flux density could be defined as irradiance, exitance. Irradiance means how much amount of flux density is energy is actually leaving that particular surface, not our surface, any surface, leaving that surface, that is called as exitance. And this flux density is defined by watt per square meter. Why? Because watt is power and you have added unit surface area, so you are getting square meter also you are adding, so watt per square meter is your flux density. When we add solid angle to flux density, okay, first we added time to energy, then we added unit surface area to that particular energy also, then we have added solid angle also to that energy, which means we have added 3 different variables. So what we got? Now we get radiance. Okay, now we get radiance. So radius is watt per meter square per steradian. Okay, so it means radiant flux or radiant density per steradian. Radiant density per steradian is your radiance, because here we have added solid angle also. Here, if we add wavelength to flux density, when we add wavelength to flux density, what we get? We get radiant spectral flux density. What is radiant spectral flux density? It means we are not talking in terms of the whole wavelength. We are talking about a narrow part of the wavelength, a very narrow part of the wavelength. So that is radiant spectral flux density, which could be spectral irradiance and which could be spectral exitance. So from this definition itself, you can make it that if we actually integrate radial spectral flux density, so what we will get? We will get flux density. When we integrate radiant spectral flux density across all wavelength, we will get flux density. So from here we can reach up to radiance. Now let's see from there what we can do. From here also, suppose radiant energy, we add time, we get power or radiant flux. To that time, if we use add solid angle, okay, time plus solid angle, what we get? We get radiant intensity. So which is watt per steradian. Okay, radiant intensity is watt per steradian. If to this watt per steradian we add area, okay, if we add area, so what we get? It means this one, unit surface area, we get radiance. So from here also we can reach up to radiance, from here also we can reach to radiance. So radiant intensity, then we get radiant flux, radiance, and then finally we get spectral radiance. What is spectral radiance? Again, it is a function of wavelength. It is for a narrow wavelength, we are measuring the radiance. Then it is called as radiant flux. Solid angle, you all might have gone through what is solid angle. So what is solid angle? The radiant intensity, which describes the flux per unit solid angle from a point source into a particular direction, is called as solid angle. And this is dimensionless. Okay, solid angle is dimensionless. So it is the ratio of this spherical area to the square of the radius. And its unit is steradian, and it is denoted by d omega. Okay, that is what is solid angle. It is your dimensionless. I'm not going through the total definition because I think if I go through all the definitions, it will take lots of time. So I'm just giving you a glimpse. You can go through my slides, and if there are any more thing that you want to discuss with me, then you can always come back to me. If you have any suggestions also, you can come back to me. Okay, we can discuss further. Okay, so it's a dimensionless property. So radiometry and radiometer. What are radiometry and radiometer? When we say radiometry are the physical measurement of electromagnetic radiation within the ultraviolet, visible and infrared wavelengths. So whatever physical measurements we are doing for electromagnetic radiation within the ultraviolet, visible and infrared wavelengths are called as radiometry. Why this concept is important? Because we have all the sensors, we have got radiometers, okay? We have spectroradiometers, and from there we actually measure the electromagnetic radiation and then we quantify it. That's what is remote sensing. What are radiometers? Radiometers are the devices which are used to measure the radiant flux or power in electromagnetic radiation. There are certain characteristics of a radiometer. What are the characteristics of a radiometer which we use for remote sensing? First of all, it should have a spectral range. It means wavelengths which we are measuring. The spectral range of the radiometer is very important. Spectral sensitivity is very important, like sensitivity versus wavelength measure. That how your spectral wavelength or range is sensitive to a particular wavelength measured. Okay. Then field of view. What is the field of view? How much area we are measuring? Okay. The field of view of the particular sensor. That is important. Like 18 degrees or limited to a certain narrow field. And directional response. It means typically the cosine response of the unidirectional response. So these are few of the important characteristics of a radiometer, which defines a particular type of sensor. So radiant energy, which is measured in joule, I already defined that it is the energy of electromagnetic radiation, and its SI unit is joule. Quantity of radiant energy may be calculated by integrating radiant flux with respect to time. So from here also we can find out radiant energy. It means if we integrate radiant flux with respect to time, what we get the quantity of radiant energy. So both way it is possible. Radiant flux or radiant power. What is radiant flux or power? The radiant flux is the rate at which radiant energy is emitted, transported, or received in the form of electromagnetic radiation from a point or a surface to another surface. So phi equal to dEq by dt. Okay, that is what is the definition. And since it represents energy per unit time, it corresponds to power. So radiant flux is basically the power of the electromagnetic radiation, and it is joule per second or watt, and it is a total power of electromagnetic radiation. So radiant flux of radiant power is the measure of total power of the electromagnetic radiation, including visible light. And spectral flux, when we talk about spectral flux, one is radiant flux, another is spectral flux. So spectral flux is monochromatic flux. Monochromatic flux means flux contributed by radiation over some small narrow in wavelength interval. Okay, so here since it is small narrow wavelength interval, so what we are adding, watt per meter square per micrometer. Per micrometer means which is actually your small wavelength interval in which we are measuring. So no information on direction of origin. Generally the radiant flux, it has got no information on direction of origin. Irradiance. Irradiance is what? Which is reaching to a surface, and exitance is which is leaving a particular surface. So irradiance, let's understand it more clearly. Like let's take the energy that is being emitted from the sun and calculate quantities for its various distance. For example, some amount of energy is emitted from the sun. It reaches Mercury. Okay, it reaches Mercury, and then it goes up to Pluto. So what will happen? The radiation has not dispersed over a very wide area when it reaches Mercury. Okay, remember the area of a sphere equals to 4 pi r square. So the smaller the radius of the sphere, the smaller the area of the sphere. So when it is reaching Mercury, so it has got a very small amount of energy which is dispersed. But by the time it reaches Pluto, r square increases tremendously. Since r square increases tremendously, so amount of radiation reaching up to the planet Pluto or dispersed up to the planet Pluto, it decreases. So if we stop the radiation very far from the sun, for example, as far as Pluto, the area covered is very much larger. So the same power is now spread over a very large area. Power is same, but the thing is now it is spread over a very, very larger area. So irradiance or radiant, your flux density depends on the distance. Closer the distance, more is the irradiance or flux density. Farther is the distance, less is the irradiance or flux density. And SI units is watt per square meter and equal to d phi by dA. Yeah. So irradiance is flux density of a radiant flux arriving at a surface, and radiant exitance or emittance is the flux density of radiant flux emitted or leaving from a particular surface. Note. What to note? The amount of irradiance decreases as we move further from the source, but the amount of radiant intensity does not. So if we move from like Sun to Mercury and from Mercury to Pluto, the irradiance will decrease, but the radiant intensity will not decrease. It will remain constant. So why? Radiant intensity now discussed. The radiant flux, radiant intensity is the radiant flux leaving a source per unit solid angle in a given direction. So the radiant flux leaving a source per unit solid angle in a given direction is the radiant intensity. So intensity remains same, but since it is dispersed, if it is going to a further distance, therefore its power decreases. So SI unit for radiant intensity is watt per steradian. I showed you that from power, if you add solid angle, you get radiant intensity from that particular flow chart. So here the SI unit is watt per steradian. If a point source radiates equally in all directions with a radiant flux phi, the radiant intensity I equal to phi by 4 pi. So that is how we can find out. This radiant intensity describes both the strength, what is the strength, as well as direction of radiation sources. The strength and direction of radiation sources are defined by radiant intensity. Radiance, when we say, it characterizes total emission or reflection. That is, spectral radiance characterizes the light at a single wavelength or frequency, and radiance is equal to the sum of all the spectral radiances from a surface. And SI units for spectral radiance are watt per steradian per meter cube when measured per unit wavelength, and watt per steradian per meter square per hertz when measured per unit frequency interval. So whether we are using frequency interval or we are using meter interval, so in both way, you can actually give different type of SI units to radiance. Satellite remote sensing measures radiance. Please remember that what type of energy we are measuring from satellite remote sensing. We are measuring radiance. Okay, we are measuring radiance. Why? Because radiance is very useful. Why it is useful? Because it indicates what? How much of the power emitted by an emitting or reflecting surface will be received by an optical system. Okay, how much power emitted by an emitting or reflecting surface, it will be received by an optical system, looking at the surface from some angle of view. So that's what we are trying to measure. Conservation of intensity. Conservation of intensity says what? That intensity does not decrease with distance from the source within a vacuum or other transparent medium. As I told, that irradiance decreases, exitance decreases, but the intensity does not decrease. Because the eyes in optical system, radiance and luminance are good indicators of how bright an object will appear. For this reason, radiance and luminance are both sometimes called brightness. So both radiance as well as luminance are called as brightness. So if you do thermal remote sensing, you will find one term which is called as brightness temperature. Okay. So remote sensing instruments, example, a satellite sensor viewing a narrow range of direction measures radiance, as I said. Yeah. So the takeaway from this much of discussion is irradiance decreases as the square of distance from the source, and radiance is invariant with distance. It means it does not vary with distance. It is independent of distance, and therefore we measure radiance. Okay. Solar constant, that is irradiance at top of Earth's surface is 1370 watt per meter square, 1370 watt per meter square. So radiance versus reflectance, because we measure radiance from satellite remote sensing, and finally we convert it into reflectance, because if we try to find out the material property, then we will have to go for the reflectance. So what is radiance and reflectance? Radiance is the variable directly measured by remote sensing instruments. It is the amount of light the instrument detects from the object being observed. When looking through an atmosphere, some light scattered by the atmosphere will be seen. So basically radiance I have already defined. Reflectance, it is a ratio of the amount of light leaving a target to the amount of light which is striking the target. So it's a basically ratio that we are trying to find out. And if all of the light leaving the target is intercepted for measurement of reflectance, the result is called hemispherical reflectance. So what is hemispherical reflectance? It means if all the light which is leaving the target is intercepted, like one target is hit by a light and then it is scattered, and then if we intercept all the lights which are actually leaving that particular target, it is called as hemispherical reflectance. Okay. One more important concept is in terms of material property. If we are talking about material properties, black body. Okay. So what type of surface it is hitting up? So black body. What is a black body? So black body is an ideal surface that absorbs all incident radiation at all wavelengths and all direction. And therefore, see, it absorbs all incident radiation, it absorbs at all wavelengths, and it absorbs at all direction. So therefore, it is called as a perfect absorber. Any black body is a perfect absorber. That's what is the definition of a black body. It has three important properties. The first property is it is a surface that emits most for a given temperature and wavelength. First property is it is a surface that emits most for a given temperature and wavelength. Second is black body radiation does not depend on the direction. That is, black body is a diffuse emitter. Okay, it's a diffuse emitter. It does not depend on the direction. Third is total black body radiation in a vacuum depends only on temperature. So the only variable on which black body radiation depends is a temperature. And since the black body is the perfect absorber and emitter, it will be used as a reference to compare the radiative properties of real surfaces. So when we study the radiative properties of a real surface, we need to have some references. So for our reference, black body is as a reference, and with respect to black body, we term everything that how a real surface is actually, the radiative properties of a real surface is actually vary. Okay. So characteristics of a black body, the spectral impedance distribution curve is continuous and shows a single maxima for any temperature. As the temperature increases, the maximum shift to the shorter wavelength. So if you look at this one, the first thing says the spectral impedance distribution curve is continuous and shows a single maxima for any temperature. So here for any temperature like 5770 Kelvin. So see, there is one particular maxima. There is one particular maxima. For 2700, there is one particular maxima. Second is the temperature increase as the wavelength maxima shift to the shorter wavelength. So from here, see, initially it was 2700 Kelvin, so maxima was here. But when temperature increased, it has migrated to shorter wavelength. When it was Earth surface, 288, how much? 100 Kelvin or 288 Kelvin. So from here, what happened? It is shifting towards shorter wavelength as the temperature is increasing. Okay, throughout the spectral range, the emittance value is higher than the lesser temperature. That is, the curves do not cross each other. So if you look at here, the curves do not cross each other anywhere. And then on the higher wavelength side of the emittance peak, the radiation decreases monotonically with increase in wavelength. That is, even at the microwave region, there is emittance from the body. Okay, these are few of the property. So the peak of the black body curve shifts to shorter wavelength as temperature increases, and this peak represents the wavelength of maximum emittance. What is the maximum emittance? If we further integrate or differentiate Planck's law of radiation, what we will get? If we integrate, we will get Stephen-Boltzmann law. If we differentiate, we will get Wien's displacement law. So let's find out first integration and then differentiation. Stephen-Boltzmann law, which we get after integrating Planck's. Yes, the study material will be provided. I think I have already shared the PPTs. Anyway, Stephen-Boltzmann law. The amount of energy an object radiates in per unit area, considering all wavelengths, can be expressed by Stephen-Boltzmann law. Okay, the amount of energy an object radiates in per unit area, considering all wavelength, that is what is Stephen-Boltzmann law. And the total emission within the wavelength can be found out by integrating the Planck's equation, lambda equal to 0 to lambda equal to infinity, and works out to be MB, which is the total radiant exitance from the surface of a material measured in watt per meter square, equal to sigma T to the power 4 for black body. And if we take real body, then we just add one more parameter, which is called as emissivity. So MB equal to emissivity multiplied by sigma T to the power 4 for real body. So which means if absolute temperature of a body is doubled, it would render 16 times more radiation. Okay, if the absolute temperature of a body is double, it will render 16 times more radiation. Wien's displacement law, which is you can't hear me. Can you hear me?
Yes.
Okay. Yeah. Someone.
Yes, you are audible, sir.
Okay. Fine. Yeah. Thank you. So Wien's displacement law, which we get by differentiating the Planck's law, black body law. Okay. So after differentiating, what we get is the temperature of a body increases, total energy radiated increases, and wavelength at which the body object emits most energy also decreases. So the wavelength at which maximum energy will be radiated or emitted is found by Wien's displacement law. This is a very important equation, like lambda max equal to B by T. So when we do thermal remote sensing, you will realize that in thermal remote sensing, suppose we are saying that we need to develop one sensor for Earth surface, another sensor we need to develop for volcanic processes. What is the temperature of Earth surface? Maybe 300 degree Kelvin. Okay, in Kelvin, 300 degree. So for Earth surface, what should be the ideal wavelength in which we should develop our sensor? So divide 2898 by 300. How much it will be? 9327. Some 9 point something value, isn't it? It means if we need to develop any sensor to study Earth surface, so what type of wavelength we need? We need to target the wavelength 9 point something. So we should develop our sensor which is sensitive at 9 point something wavelength. Okay. And if we are studying volcanism, so what could be the temperature of a volcanic processes? It could go up to say 700, 800, okay, 600, okay. So if it is 600 degree Kelvin volcanic processes, so 2898 divided by 600, how much it will be? 4 point something, 4.89, something like that. So it means if we want to develop one sensor for volcanic processes, what type of wavelength we need to target? 4 point something, 4 to 5 micrometer. Earth surface, 9 to 10 micrometer. Then if we study volcanic processes, 4 to 5 micrometer. So that is what we are actually targeting. Emissivity, as I said, there is one factor, emissivity. What is emissivity? Emissivity is how close a body is to black body is defined by how close a body is to black body is defined by a figure of merit called spectral emissivity, which is the ratio of the emittance from an object at a given temperature to that of a black body. Okay, that is what is emissivity. And this can vary with respect to wavelength, and sometimes it can vary with respect to temperature also. If it varies with respect to wavelength, we call it a selective radiant. If it does not vary with respect to wavelength, we call it as gray body, where emissivity is less than 1, but it remains constant across all wavelengths. So if we look at this particular figure, you will find out spectral emissivity of black body, it varies with respect to wavelength. Gray body, it remains constant, although it is less than 1. And the black body is absolutely 1. Okay. This emissivity depends on color. Darker objects have got higher better absorbers and better emitter. Lighter objects are actually a poorer absorber and poorer emitter. Surface roughness increases, emissivity increases. Moisture content, compaction, field of view, wavelength, all these things actually defines the emissivity. There is one particular table that I have shown here, which tells about the average emissivity of some objects in the 10 micrometer range. So what are the different emissivity properties? So in summary, we could say that as T increases, so does lambda max increases. As T increases, the wavelength of maximum emission decreases or shifts to shorter wavelength from Wien's displacement. We could find out. Considers Wien's law for the sun, 600 degree Kelvin, lambda max is 0.483 micrometer. It means if we want to study the sun, then we need what? We need 0.483 micrometer range in which it is best studied. If we want to study Earth, 300 degree Kelvin, we need 9.66 micrometer, which is ideal. As objects are heated, they change colors. As at low temperatures, lambda max shifts to shorter wavelengths. So all these are the takeaway from this particular lecture. Quickly now, I'll go to the atmospheric interaction of electromagnetic radiation. Actually, this lecture is of 2 hours, but it needs some 3-4 more hours to discuss. So many things are there, which gives a prelude to basic remote sensing. So let's study about the atmospheric interaction. As I said that from sun, the energy is reaching up to the surface of the earth, but in between there are lots of things happening. That is the gases present or the molecules present in the atmosphere, they interact in different ways. There could be some amount of absorption by water vapor, there will be some amount of absorption by cloud, there could be some amount by reflection by cloud, backscattering by air, reflected by surface, okay? At night time, what can happen? Emission by water vapor, carbon dioxide, ozone, emission by cloud, latent heat transfer could be there, sensible heat transfer could be there, absorption by clouds, water vapor, carbon dioxide, ozone. All these things can actually take place, okay? So what are the atmospheric effects? Atmospheric effects are EMR interact with atmospheric gases like carbon dioxide, water vapor, ozone, and suspended material like aerosols, dust particles, etc. So with all these things, it interact. For example, you might have seen one very good concept which came out because of this lockdown, that many cities in Europe, actually the aerosol particles decreased to a great extent, because of which the urban heat island has actually increased in those cities. Many cities got heated up because there were no aerosols, so whatever energy was there, it was targeting the earth's surface, it was reaching earth's surface. So during interaction, it gets partially scattered, absorbed, transmitted, and emission. Atmospheric effects are there. There could be scattering, there could be absorption, there could be transmission, which is actually reaching the earth's surface, or there could be emission also. There are few definitions like path radiance, ground radiance, and path length. What is path radiance? The part of the signal which is emanating from the atmosphere is called as path radiance, and it masks the ground signal and acts as a background noise. So path radiance is basically background noise. Ground radiance is part of the signal which is emanating from the ground. So we are interested in ground radiance if we are not doing atmospheric studies, if we are doing the study of the earth. Degree of atmospheric interaction depends on path length and wavelength. So what is path length? Is the distance traveled by the radiation through the atmosphere and depends on the location of the energy source and the altitude of the sensor platform. So role of atmosphere. As I said, the role of atmosphere is that what it does, the sun's energy is altered in two phases. First is it can alter the intensity of the sun's energy, or it can alter with respect to wavelength also, by particles and gases present in the Earth's atmosphere. And these changes appear on the image in ways that degrade image quality or influence the accuracy of interpretation. So because of the atmosphere, like it alters the intensity or the wavelength, because of that, there will be some amount of degradation of the image that we are getting from remote sensing. So for passive reflective remote sensing and active microwave remote sensing, energy must pass through the atmosphere twice. Okay, if we consider the reflective energy as well as the microwave remote sensing, active microwave remote sensing, the energy should pass through the atmosphere twice. But for passive thermal and passive radar remote sensing, energy must pass through the atmosphere once. So if we are considering thermal remote sensing, it is traveling through atmosphere once, and passive radar remote sensing is traveling through atmosphere once. But passive reflective and active microwave, it is traveling through atmosphere twice. Please remember. So it means that much of distortions will be there, or degradation will be there to that particular energy source, whatever we are measuring. So all solar energy passes through the Earth's atmosphere, and it is subjected to modification by several physical processes, which could be classified as scattering, absorption, reflection, and diffraction. 4. Scattering. So scatterings are like elastic scattering. What are elastic scattering? In which the energy of radiation is not changed due to the scattering. So when the energy of radiation is not changed by scattering, we call that as elastic scattering. But if energy of the scattering is changed, we call it as inelastic scattering. The elastic scattering could be defined in two groups. One is selective scattering, another is non-selective scattering. Selective scattering means it is wavelength dependent. Non-selective scattering means it is not wavelength dependent. Simple. Within selective scattering, there are three: Rayleigh scattering, Mie scattering, Raman scattering. Non-selective scattering, one only. So what is scattering? Is the redirection of electromagnetic energy by particles suspended in the atmosphere or by large molecules of atmospheric gases. And the amount of scattering that occurs depends on the size of this particle, their abundance, wavelength of the radiation, and the depth of atmosphere through which the energy is traveling. Okay, so based on that, we have Rayleigh scattering, Mie scattering, etc. And this graph shows actually how it looks like. Rayleigh scattering. Rayleigh scattering is named after Lord J.W.S. Rayleigh, who actually demonstrated a perfectly clean atmosphere, and it is the amount of scattering increases greatly as wavelength becomes shorter. And because of Rayleigh scattering, the sky appears blue, the water also appears blue because of Rayleigh scattering, and blue light is scattered about 4 times as much as is red light, and ultraviolet light is scattered almost 16 times as much as is red light. So as we go towards shorter wavelength, the Rayleigh scattering increases tremendously, and that is why in visible band, blue color is actually, whenever we do remote sensing, we try to avoid blue color, the blue part of the wavelength. Why? Because it is always oversaturated. The image looks blue in color. Okay, it looks blue in color, and therefore we try to avoid the blue color part of the spectrum. Okay. Yeah. So effect of remote sensing images, because of Rayleigh spectrum, what will happen? Multispectral remote sensing data from the blue portion of the spectrum is of relatively limited usefulness. And in case of aerial photography, spatial filters are used to filter out the scattered blue radiation due to haze present in the atmosphere. Mie scattering. Mie scattering, what it does is caused by large atmospheric particles, including dust, pollen, smoke, and water droplets. And here the particles that cause Mie scattering have diameters that are roughly equivalent to the wavelength of the scattered radiation. And it is also wavelength dependent and tends to be greatest in the lower atmosphere where larger particles are abundant. And effect, what type of effect it will have on remote sensing images? Mie scattering will usually manifest itself as a general distortion of multispectral images across the optical spectrum under conditions of heavy atmospheric haze. Non-selective scattering actually it affects across all the wavelength, and that is why clouds, what will happen, the droplets of water in clouds, so cloud will be reflected equally in visible band, in sphere band, in infrared band. Everywhere it will be scattered equally. Why it will, and when it will be scattered equally, so blue will be scattered, green will be scattered, red will be scattered. Together if we club, we get white color, and therefore cloud appears white, and cloud has got white color, means not only white color but equal reflectance across, scattering across all the wavelengths because of non-selective scattering. Therefore cloud appears bright. Yeah, non-selective selective scattering are caused by much larger particles than the wavelength, and where all wavelengths are scattered equally. And effects of scattering are that it causes haze in remote sensing images, it decreases the spatial detail of the images, it also decreases the contrast of the images. Second is the water droplet. So water droplet with diameters ranging from 5 to 100 micrometers scatter all wavelength of visible light with equal efficiency. As a consequence, clouds, fog, they always appear whitish because of mixture of all colors in approximately equal quantities, which produce white color. Okay, so this is what is a table which summarizes everything: the Rayleigh scattering, wavelength dependence, Mie scattering's wavelength dependence, non-selective scattering is not wavelength dependent, and particle size, whatever particle size are affected, kind of particles which does the all this effect. So second part is the atmospheric window. So what is atmospheric window? We can't do remote sensing across all the wavelengths. We can do remote sensing only narrow wavelengths. For example, for ultraviolet rays and lower, the smaller wavelengths, we can't do remote sensing. Why? Because it is absorbed by the atmosphere. Visible part is highly has got higher transmissivity. And sphere bands, very near infrared bands or sphere bands, it has got lower transmissivity because most of the radiations are absorbed by what? It is absorbed by carbon dioxide or water molecules. For example, this is these three highlights: very high for wavelength 0.3 to 1 micrometer and greater than 1 centimeter. This part is highly transmissivity or transmission is highest. Moderate transmission or good transmission is for 1 to 20 micrometer and 0.1 to 1 centimeter, and very poor for less than 0.3 micrometer and 20 to 100 micrometer. So these are the three different ranges which are very high, moderate, and very poor transmissions are there. And wherever transmissions are there, these are the atmospheric window where we can do remote sensing. So these are the major atmospheric windows for ultraviolet and visible, near infrared, thermal infrared, and microwave. We can remember this thing, and we can do remote sensing only in this part. We can't do remote sensing in any other part for terrestrial remote sensing, not for planetary. For planetary, because there is no atmosphere, there is no problem. If we are doing Chandrayaan studies or data study, or if you are studying lunar surfaces or Mars surfaces, there is no problem. Absorption. So absorption, there are three types of absorption. One is because of ozone, second is because of carbon dioxide, and third is because of water molecules. Among them, water molecule is the most important because it has got the highest absorption. I'm not going into that details because time is very limited. Refraction. Within atmosphere, because of different air columns, there could be refraction also. So what is refraction? Bending of light. So when light passes from one medium to another, it can bend. So similarly, since there are two different densities of air columns, so there could be refraction within that. And atmospheric shimmering is produced by movement of masses of air within different densities. So if different density of air columns are actually moving with respect to each other, so what it can do, it can produce blurring of your images in satellite images. Reflection, okay? Reflection is the bouncing of surface, whatever energy is reaching to the surface, whatever is bouncing back, it is the reflection. Interaction with surface. So what type of interactions are there with the surface? There are three types of interaction: absorption, transmission, and reflection. What is absorption? Radiation is absorbed into the target. What is transmission? Radiation passes through a target, and reflection is radiation bounces off the target and is redirected. So there are three things which is happening with the interaction with the surface: absorption, transmission, and reflection. Okay, the portions of each interaction will depend on the wavelength of the energy and the material and condition of the feature. So it's not that one particular surface will behave same for all the wavelength. It is wavelength dependent. In few wavelength there will be absorption, few wavelength there will be transmission, few wavelength there will be reflection. Yeah. Specular and diffuse reflection. What is specular and diffuse reflection? So when a surface is smooth, we get specular or mirror-like reflection. So whatever energy is reaching, it will be in one direction, it will be reflected back. So we get mirror-like surface, and it means it will look very bright. Diffuse reflection means when the energy is striking a surface and it is actually scattered in all directions. It is reflected almost uniformly in all directions, or it is reflected in diffuse, scattered in all directions. So then it is called as diffuse reflection. Diffuse reflection contains information on the color of the reflecting surface, whereas specular reflection does not have any information on the color of the object. Therefore, as a remote sensing person for geology or for the Earth surface, not for atmosphere, we are more interested on diffuse reflection, not on specular reflection, because specular reflection gives very less information about the particular material, but diffuse reflection gives most information about the particular material. Okay. So reflection from the surface, it depends on direction of incident ray, nature of the surface, wavelength of the incident ray. So there are specular reflector and diffuse reflector, as I defined. Different types of reflectors could be specular reflector, diffuse reflector, hotspot reflector, nearly specular reflector, and nearly diffuse reflector. I can do one thing at the end of this lecture. I have some 2-3 video lectures that I prepared. I think I have uploaded in YouTube also. All these informations are there. I can share it because those are actually some 3-4 hours of lecture which contain all the information. So you will be more benefited because now I am going very fast, I feel. Yeah, so Rayleigh criteria of roughness. I'm skipping it because I can give my lecture videos that you can go through. What is Rayleigh roughness of coefficient, criteria of roughness? It means how do we define the roughness of a surface? Whether a surface is smooth or it is a rough surface. So it is defined by one formula, which is delta H should be less than lambda by 8 cos theta. Okay, and there are 2 problems that I have defined in my particular lecture also. So there are different, like Peake and Oliver's modified Rayleigh criteria of roughness is also there. Lambertian reflector and diffuse reflector, all these things are defined there. You can go through those things. So what does the sensor require? It requires spectral radiance. Not only radiance, it acquires spectral radiance, because in narrow wavelength, we acquire the information. And this radiant flux in a beam per unit wavelength and per unit area and projected solid angle of a beam, that is SI unit is watt per meter square per steradian per micrometer. Okay, and if it is for frequency, then we will use hertz. The reflectance, it is the ratio of the radiant excitance with the irradiance. Okay, what is the ratio of the radiant excitance with the irradiance is your reflectance. And the reflectance is a ratio of radiant flux, hence it is dimensionless. Reflectance is dimensionless. I told you that we try to find out the reflectance also. And this reflectance could be spectral or it could be directional also. Yeah, I'm skipping these parts. My slide I'll be sharing. You can read through all these things. Very clearly written everything, or you can go through my video lecture also later on. Spectral reflectance formula, all these things. So I'm skipping this. thing. Okay, these has got lots and lots of information actually. Spectral reflectance signature. What is spectral reflectance signature? Any object can behave differently to different wavelength. Like there will be certain amount of transmission, there could be certain amount of reflection, there will be certain amount of absorption. That is the signature of the particular material, that how that particular material behaves across different wavelength. So when we know the spectral signature of a material, we can easily identify that material if it is present in some other area from the remote sensing images. Okay. So yeah, this is the spectral reflectance of a vegetation, how it looks like. For example, if you look at the vegetation, so there are some two dips in visible band in blue and red. These two dips are because of chlorophyll absorption bands, and then there is a huge crest. It means in infrared band it has got highest reflectance, and again there is a dip because of water absorption, and then again there is a crest here, again a trough, again a crest. So all these things are because of atmospheric water absorption bands. This one are because of atmospheric water absorption bands. So these are the spectral reflectance signatures. So I'm skipping all these things. Then comes your types of bands. So I'll just quickly go through different types of remote sensing products. So one product would be your black and white infrared images. What are black and white infrared images? Those images which are acquired in a near infrared region are called as black and white infrared images. Why these images are important? These are important because it largely, they are free of effects of atmospheric scattering. It means relay scattering or Mie scattering. This shows vegetated region and land water distinction. It means if you want to go for land water distinction, or if you want to study vegetation, so this was a gate question some 1 or 2 years back. So for that we need black and white infrared images, or the infrared band helps us to find out this thing. And it is one of the most valuable region of the spectrum because it is not affected by any type of scattering, means relay or Mie scattering. And SWIR band has shadow and contrast due to reflective nature. It means infrared images, if it is in reflective domain, they are affected by shadow as well as contrast, okay, because they are reflected energy. Panchromatic bands. When we say panchromatic bands means across the bands. So when we collect information across the bands, it means from visible 0.34 micrometer to 0.7 micrometer, it is called as panchromatic bands. Here chromatic means color. So when color concept is there, so it is basically for the visible band. But nowadays what we do, we remove the blue band because it because of relay scattering, it creates blurriness. Therefore we remove the blue band and we consider little amount of the SWIR band. So panchromatic band means now remove the blue band and consider little amount of the SWIR band also, so that you get sharper and clearer images. Okay. Multispectral remote sensing. Multispectral remote sensing means if we are doing remote sensing in different wavelengths, okay? If we are doing remote sensing in different wavelengths, then we call it as multispectral remote sensing. Why we do remote sensing in different type of wavelengths? Because it helps us to spectrally separate. There is a spectral separation. What does multispectral remote sensing help us to do? It helps us to do spectral separation. We can spectrally separate different type of objects. So because of the spectral separation, it gives us an advantage, okay? So, for example, this particular figure, if we look at means percentage reflectance at 0.85 millimeter and percentage reflectance at 0.55, not millimeter, micrometer. So what we will get? So for different type of objects, we will get spectral separation. So if we do means one band by another band, if we plot, we will get different objects in different part of this particular plot. So this is what is spectral separation. This is what is the most important factor in case of multispectral remote sensing. We do remote sensing based on spectral separation. In case of hyperspectral, when we say hyperspectral remote sensing, it essentially means that the data should be narrow and contiguous. What is contiguous? It means narrow should be how much narrow? 0.5 micrometer to 0.10 or 0.15 micrometer up to, okay, 0.05 micrometer to 0.10 or 0.15 micrometer. 5 nanometer to 10 nanometer or some 15 nanometer. That is what is a hyperspectral, that narrow, actually that much of narrow we are considering. But in case of multispectral, it goes up to 100, okay, it goes up to 100. So here the bands are narrow. How much narrow I told you, and it should be contiguous. What is contiguous? Contiguous means it is equally spaced, one after another. It is equally spaced, and therefore we get lab spectra. We get which is actually the remote sensing spectra that we get is equal to the lab spectra. I think the people who will be discussing the hyperspectral remote sensing will tell you more about this particular thing. Swath of satellite image. Swath of satellite image means how much the the width is covered, how much footprint is covered, how much width is covered. So that is the swath of the image. For example, for Hyperion image, the swath is 7.5 kilometer. For the resource set list 4 data, it is 75 kilometers. So that is what the swath of the satellite images. Instantaneous field of view, it means the spatial resolution, it depends primarily on the instantaneous field of view, and it's the angular cone of visibility. So depending on the IFOV, smaller is the IFOV, larger will be the spatial resolution. Pixel size calculation, this is a very rough way of calculating pixel size. So pixel size is defined as 2h10 beta by 2, what is 2h10 beta by 2. So h is the distance from the ground and beta is the IFOV by 2. So from this definition, we get to know IFOV is smaller, pixel size larger, and if the distance from the earth is more, pixel size will be less. Okay. Another view, if you are viewing from the top. So resolutions. Resolutions are the ability of a system to render the information at the smallest discretely separable quantity in terms of distance, which is wavelength band of EMR, time, and radiation. So resolutions could be spatial, spectral, radiometric, and temporal. Okay, what is spectral resolution? It is the part of the electromagnetic spectrum which is measured. Radiometric resolution, smallest difference in energy measured. Spatial resolution, smallest unit area measured, and temporal resolution is the revisit time. So let's discuss one by one. Spatial resolution. What is spatial resolution? Spatial resolution is how much actually ground surface is represented by 1 pixel. Okay, if smaller part of the ground surface is represented by a smaller pixel, higher spatial resolution. Conversely, it is lower spatial resolution. So if you are doing a ratio scale if you are using, so how to find out that if you have certain pixel resolution, how you can convert it to ratio scale? So for example, if you are using say Landsat data of 30-meter resolution, so what type of scale in which you can map? Ratio scale. So it can be found as 30-meter spatial resolution of Landsat data equal to 2000 multiplied by pixel resolution gives the scale. So it means 2000 multiplied by pixel resolution is 30 meters. So 2000 into 30 meter equal to how much? 60,000. So when we use Landsat data of 30-meter resolution, you can do mapping at 1:60,000 scale. Okay, you can do mapping at 1:60,000 scale. So for example, tomorrow if you're working in some particular project, someone tells you that we want to do mapping of this particular area in 1:50,000 scale. So what should be the pixels resolution? Now you know, just simply multiply 2000 multiplied by pixel resolution equal to your scale. So if you know the scale, so now you can actually deduct that what should be the pixel resolution. Spatial resolution gone. Yeah, spectral resolution. What is spectral resolution? Spectral resolution is the narrower the spectral domain in which we are measuring the data, higher is the spectral resolution. So it is actually the smallest bandwidth. The smallest is the bandwidth, higher is the spectral resolution. Remember. Okay. So this was one of the exercise that I could have given you, but I'll skip it because time is less. So otherwise it will define very nicely. Radiometric resolution. This is a sensitivity to a smaller difference in the radiation of an observed object. And it tells that how well does the data record subtle difference in the amount of EMR reflected. For example, 2-level data or 16-level of data. So if 2-level of data, you get only black and white information. If 16-level of data, it means you get the grayscales also. So you can infer better. So we always go for better radiometric resolution. Temporal resolution, it is the exact same area at the same viewing angle. How frequently you can repeat your view. So that gives the temporal resolution of your data. So I think with this, I am actually stopping my lecture here itself. I have taken a little bit more time. So now I'm open to your questions.